Assalamualaikum. Let's continue our lesson for chapter 5. Basically, in previous lecture, we have learned how to set the back pressure, back pressure for converging nozzle in order to get the maximum velocity, which is Mach number equal to 1, based on the back pressure that we have set. Okay, so if you notice that for the converging nozzle, the highest velocity only limited to sonic velocity, which is Mach number equal to 1, and then this only occurs at the exit plane or throat of the nozzle. Okay, so if let's say as you can see in this rocket, okay, for this rocket we need a really high thrust in order to launch the rocket. Okay, so in order to have this kind of velocity, we need to increase that velocity beyond sonic, which is to supersonic velocity. Okay, so in order to achieve this, we need to we need to connect our converging nozzle to a diverging nozzle. Okay, so in this case, still the back PB, which is back pressure, is still a very important parameter that we need we need to properly set in order to get in order to accelerate the fluid. Okay, so accelerating a fluid to supersonic velocity, which is Mach number greater than 1, can be accomplished only by attaching a diverging flow section to the subsonic nozzle at the throat. Okay, a converging diverging nozzle, which is standard equipment in supersonic aircraft and rocket propulsion. Okay, so similar to converging nozzle, okay, so we need to identify what happened when we set the back pressure, what happened at the throat. Okay, now before this, for the diverging nozzle, it is only at this condition, which is P exit equal to PB. It is depend on the what we set to the back pressure. But now we have another diverging section. Okay, so this is P exit, and this is PB, which is back pressure. Okay, so the first this is the schematic diagram. We have V equal to 0, inlet velocity equal to 0. So what happened when the inlet velocity equals to 0? So the inlet pressure, inlet temperature, inlet density, for example, it is equal to stagnation temperature, stagnation properties. Okay, because the velocity equal to 0. So there is, you have always remember what happened at the inlet of your nozzle. If the velocity is set to be 0, so that the pressure, the temperature, the density at the inlet is can be set equal to the stagnation properties. Okay, so now this figure, it is pressure versus the coordinate, or the versus the x, which is the coordinate system for the nozzle, and then this is this figure, it is Mach number versus exit condition in x direction. Okay, so first we have pressure at A, B, C, D, E, and then F and G. Okay, so first we set the pressure. Okay, in first case A, we set the pressure, back pressure equal to P stagnation, P inlet, or P 0. So as usual, there are no pressure difference. Of course, there are no flow. Okay, so that's why you can see there are no variation of flow, and then Mach number also 0. Okay, so no flow, no mass. It is very simple relation. Okay, now when we set back pressure, okay, when we set back pressure less than P0, okay, less than P0 but greater than PC, okay, which is at B. Okay, it is less than P0 but greater than P at C. Okay, so what happened, as you can see, first the pressure decrease, okay, pressure decrease in the converging section. Okay, so this is converging, and then this is diverging section. Okay, first pressure decrease to minimum area, which is at the throat, and then after passing the throat, the pressure increase. Okay, so that was for the pressure. And then in terms of Mach number, it is first Mach number will be increased. Okay, Mach number will be increased, and then after the throat, Mach number will be decreased. Okay, so this is simple relation based on our previous lecture for the subsonic through relation of area velocity or relation of area pressure. Okay, so this is where we set back pressure equal to PB. Okay, so now what happened when we set pressure equal to PC? Okay, so now we set back pressure PB equal to PC. Okay, so when we set this pressure, first pressure will decrease to the sonic pressure. Okay, so this is P star, decrease to the sonic pressure and then increase. Okay, so the throat pressure becomes P critical, P star, and then the fluid achieve sonic velocity. Okay, so since it is now at P star, so the velocity now it is at sonic velocity, but the diverging section of the nozzle still act as a diffuser. Okay, slowing the fluid to subsonic velocities, and then the mass flow rate that was increasing with decreasing PB also reached its maximum value. Okay, so this is where if you remember the choke condition, okay, where we got the mass flow rate, okay, reach the maximum value. Okay, now we set back pressure less than PC, okay, less than PC but greater than PE, which is at D. Okay, this is at D. So at D, okay, so at D, the fluid that achieve a sonic velocity at the throat continues accelerating to supersonic velocity. Okay, so accelerate to supersonic velocity, as you can see, accelerate to supersonic velocity, and then in the diverging section, as the pressure decrease, okay, pressure decrease, this acceleration come to sudden stop. Okay, so accelerate and then come to this point, which is sudden stop, as a normal shock develops at a section between the throat, okay, between this throat and exit plane, so which cause a sudden drop in velocity. Okay, sudden drop in velocity, okay, and then sudden increase in pressure. Okay, so then the fluid continues to decelerate. Okay, continues to decelerate further in remaining part of the converging diverging nozzle. Okay, so for the converging diverging nozzle, the effect of back pressure, we come up with another condition, which is normal shock. Okay, so what happens if we keep decreasing the pressure below PD? Okay, so when PB less than PE but greater than P0, the flow, okay, here the flow in the diverging section is supersonic. Okay, the flow in diverging section, this one, diverging section is supersonic, and the flow expand to PF, pressure F, at the nozzle exit with no normal shock. So normal shock is not happen after PD. Okay, so thus the flow through the nozzle can be approximated as isentropic. Okay, so when PB equal to PF, you can see that when bed pressure equal to PF, no shock occurs within the outside the nozzle, and then when PB less than PF, okay, irreversible mixing and expansion wave occur downstream of the exit plane of the nozzle. And then when PB greater than PF, however, the pressure of the fluid increase from PF to PB irreversibly in the wake of the nozzle exit, creating what I call oblique shock if PB is set greater than PF. Okay, so that is what happened when for the converging and converging connected to the diverging nozzle. Okay, so normal shock will happen when we set pressure PB equal to PD. Okay, this is PB which is less than PC but lower than PE. Okay, so normal shock will be happen. Okay, so to make this subtopic easily understood, we try to answer this example. Okay, so air enters a converging diverging nozzle shown in this figure at 1 megapascal, so and 800 Kelvin with negligible velocity. Okay, so what happened? Negligible velocity, temperature at the inlet, pressure at the inlet is now automatically turns to stagnation properties. The flow is steady, one-dimensional and isentropic with K equal to 1.4. For an exit number of Mach number 2, okay, Mach number 2 is set to 2, supersonic, and a throat area of 20 centimeters square, or equal to 20. Okay, determine a throat condition, mean that P throat, for example, the throat is given T, temperature at the throat, rho for the throat, and then the exit plane condition, which is P exit, T exit, rho exit, and then mass flow rate through the nozzle, M dot. Okay, so to solve for this problem, okay, first exit Mach number is set to be 2. Okay, mean that at throat condition there are Mach number equal to 1. Okay, so at A, at throat, Mach number equal to 1. Okay, so at Mach number equal to 1, we can find all these pressure, temperature, and rho based on equation. Okay, based on equation, or by referring to the table in the appendix of your textbook. Okay, so how to say this is example for table A13, one-dimensional isentropic compressible flow function for an ideal gas with K equal to 1.4. Okay, so now at the throat, okay, at the throat, Mach number is equal to 1. Where is Mach number 1? This is Mach number equal to 1. Okay, so this is Mach number equal to 1. Okay, so this is what we call critical condition, critical properties. Okay, so let's say you want to find pressure at throat. Okay, so pt over p0 equal to 0.5283. Okay, and then t throat over t stagnation equal to where is it? 0.8333, and then rho throat over rho stagnation 0.6339. Okay, so all this can also be determined based upon this equation. Okay, so you just set Mach number equal to 1, so you will get the same or similar answer. Okay, so to find throat, P throat or P critical, you just multiply with stagnation pressure. So stagnation pressure is given 1 megapascal, and the stagnation temperature also given, so this is where you get the answer for throat condition. And then if you want to find velocity at the throat, it is 517.5 meter per second. Okay, and then for B, find the pressure, temperature, rho at the exit. Okay, same at the exit because the Mach number is given at the exit. For B, Mach number is 2. Okay, so you just use all this value in order to find that pressure, temperature, and temperature and density. Okay, so this is how to get to calculate the answer. Okay, and then you will get the velocity at the exit is this. Okay, and then C, required you have to calculate the mass flow rate. So mass flow rate equal to, you can find at any location. You can find at the inlet, you can find at the throat, and you can find the exit, the mass flow rate at the exit. Okay, so for this example, it is a mass flow rate at the throat condition, rho star, A star, and B star equal to 2.86 kilogram per second. Okay, so the flow is steady, so mass flow rate at any location is equal. Okay, so that is isentropic for converging, diverging nozzle. Okay, I think that's all, and then I will for the next lecture, it is about the shock wave and expansion wave. Okay, so see you.